So let's do an example here. So we can say that the standard cell potential equals positive 0.48 volts for the galvanic cell based on, and the equation we're given is 2 aluminum solids plus 3 Mn2 plus in aqueous solution in equilibrium with 2 aluminum 3 pluses in aqueous solution plus 3 Mn solid. We want to calculate the E cell when the concentration of manganese 2 plus is equal to 0.5 molar and the concentration of aluminum 3 plus is equal to 1.5 molar. And this is at 25 degrees Celsius. So we can set up our equation here where our overall cell potential is going to equal the standard cell potential, which was given in this case to be positive 0.48 volts, minus 0.0592 divided by N. And in this case, we can do two things to calculate N. The first is break it into two oxidation and reduction half reactions. Or we can look at this overall reaction here and try to figure out how many electrons are transferred. The number of electrons transferred in the oxidation half reaction has to be equal to that same number for the reduction half reaction. So if we look at this reaction right here, we have aluminum solid going to aluminum 3 plus. When that happens, we have to have 3 electrons in that process. But from the balanced coefficients, we have 2 of each of the aluminums. So if you have 3 electrons being transferred in with 1 mole of each of those, if you have 2 of them there, we're going to have a total of 6 electrons. With the manganese 2 plus, you have manganese 2 plus going to manganese. That's going to be a difference of 2 electrons. We have a coefficient of 3 there, so that's also going to give us 6. So in this case, you could break the things down into an oxidation and a reduction half reaction. But if you look and see the number of electrons that are transferred, you don't have to specifically break that down, so it can save you a little bit of time. So our N in this case is going to be 6. This is going to be multiplied by the log of Q. In this particular case, for this reaction, Q is going to be the concentration of aluminum 3 plus squared divided by the manganese 2 plus to the 3rd power. So when we take the log of Q, that's going to be the log of 1.5 squared divided by 0.5 to the 3rd power. And let's think about what we're doing here. We are increasing the concentration of aluminum, and we're decreasing the concentration of manganese. So if we look at this equilibrium expression here, if we increase the concentration of aluminum, the equilibrium should shift to the left. If we decrease the concentration of manganese, the equilibrium should also shift to the left. So in this particular case, both of these are going to shift this equilibrium to the left and make the reverse reaction more spontaneous. So we would predict a drop in voltage when this happens. If you go through and you calculate this, the standard cell potential is going to equal positive 0.47 volts. And you may look at yourself and wonder, geez, man, we did all this work to get 0.01 volts. It's really not that great. One of the things I want to emphasize here, and remember, chemists are nerdy people. when we see relationships like this, we think it's kind of cool. Even though there's a small little change, we can start thinking about bigger picture things. So we have a small change here, but what I want to emphasize is, let's just say you're a company and you're trying to design batteries, and you want to figure out how to increase the voltage of a particular battery. The best thing that you can do to manipulate that voltage is change the anode and cathode reactions. Because by doing that, you look at the E-cell table, the reduction potential table in the back of the textbook, it goes in a wide range of numbers. If we want to use a specific anode and cathode reaction and just manipulate the concentrations, manipulate the partial pressures, all of that kind of stuff, we're not going to get very far, because it kind of sucks that this term over here is 0.0592. Then we have to divide that by the number of electrons that are transferred. So we have a tiny, tiny number that we're dealing with here. So you're not going to see a huge jump in voltage when you try to manipulate these reactions. When we were redoing the general chemistry labs, one quarter when we first tried to do this, I had this bright idea that I'm going to give these students a lab practical, right? So they had a task to do, and I had them change the voltage by a pretty decent jump, and like no one could do it because they couldn't dissolve enough copper sulfate in water to get the concentrations high enough, right? So it's not a very realistic expectation if you're a corporation and you're wanting to change the potential to try to manipulate the concentrations. And also, in doing so, we can increase this potential right here by jacking up the concentration of the aluminum 3+ and lowering the concentration of the manganese 2+. If we're making a battery, we need to make it run for a decent amount of time. So as soon as that manganese 2+ concentration reaches equilibrium, battery's not going to work anymore. It's going to be dead. So we want to be able to have large concentrations of both the cathode and anode concentrations to make sure that battery runs for a decent time. Okay, and we'll talk about that a little bit later this week. So this is how you would manipulate a cell potential under non-standard conditions.